What's up, guys? I'm very happy to tell you that I'm starting this reactor engineering course. By the way, if you haven't checked my webpage, go here. I will be adding here a link. So go to Chemical Engineering Guy and you can find the course already there, or at least one section of it. So we're going to see this slideshow, which is RE0. It stands for Reactor Engineering and block number 0. It's just the overview of the course. So if you are interested in what we're going to see in this course, you don't need to check out every video, just check this one, and if you think something is useful, go and check it. So the first thing I want to show you is the index content, which is essentially the importance of the course. Why do we need to take this course, or why is it important for chemical engineering? And then we see some books, the textbook references, and we actually have 3 books in chemical engineering. Well, we have a lot, but the 3 main books I'm going to show you here, and then I'm going to show you which one is the one I picked for this course. Now it comes basic concepts that you already need to know. So if you have problems with chemistry, balancing equations, or you don't know how to take the limiting reactant, excess reactant, all those stuff, please go and check them here. If you don't know how to do it, maybe you're going to have a bad time here, so please go check it and see if you already know it and if you have mastered that, and if not, go back and review those courses. Now, of course, we go to the main content of the course. It's essentially how I structure it and some like direct chapters we're going to see of that book. And at the end, I show you some notes and more information in case you want more. So let's start with the importance. So probably you know chemical engineering implies reactions. Those reactions take place normally in a reactor, industrial reactor, depending the size of the process and all that, of course. And in reactor engineering, we're going to see how to design and to operate those reactors. So many people tell me, why should I study if I'm going to work in a plant or something, in a factory? Well, maybe then you just need to know how to operate it. And if you are doing the plant design, or you're starting from the basic engineering concepts or whatever, you will of course need to know how do you design a reactor. So essentially is you get something inside that reactor, you're going to transform it, and then you go and get those new products. So these products of course have a value in the market, so I think the idea is to get not so expensive materials and turn them into super expensive or profitable materials. Now, I like giving this course because it's the most chemical, or that involves more chemistry. This unit operation of reactions is, I think, the typical difference between a mechanical engineer and a chemical engineer. Because a mechanical engineer can actually also show you how to pump, how to compress, how to add heating to a system, cooling, condensation. Maybe he can do that, but what he cannot do and a chemical engineer can actually do is a reactor or a system of reactions. Understand kinetics, how do they react, how do you get more of the product, how do you improve conversion, whatever. So yeah, that's why I like this course, and I think if you were, well, at least was my case when I was starting chemical engineering, I always dreamed on doing my chemical reactors and exploding stuff and all those kind of things. So yeah, it's very important at least to understand it. If you cannot design it, it's okay, but if you understand the process, what's happening, why do you get stuff inside, why do you react them that time and in that volume to get that conversion, I think you are already having an idea of what we're talking about in the chemical engineering world. And yes, I have these 2 pieces. We're going to see isothermal and non-isothermal designs. Isothermal is easy because there's one temperature. Non-isothermal is not that easy because you have temperature changing, so take care in that. And then we go to steady and unsteady states. Now we're going to see the understanding of the many concepts involved in reacting materials, such as conversion, selectivity, the Arrhenius equation, temperature dependence, rate of reaction, molar balances of reactors, plug flow, reactor, continuous stir tank reactor, drop of pressure, all that stuff. We're going to see them. And of course we want to improve our process by changing process variables for, I don't know, maybe I told you before, increasing a conversion, a selectivity of a product, and what, etc. So also know at least which type of reactors are available on the market or in the industry. So maybe you don't have any idea. The most typical one is the batch reactor. You put stuff there, you react it, and you take out. If you're working in a continuous process, you get some stuff in, you react it, and at the same time you take out the process. But you have many other types. You're going to see also where there's a flow, it reacts as it moves, and then it goes out. Many other reactors we're going to see in the other classes. Now you got to be good, or at least know some kinetics and rate of reactions. So if you're not good in chemistry, or you are having bad time on chemistry, stoichiometry, all that, we're going to make a small review, but of course the class is not about kinetics, or at least not that much. It's just to understand and then apply them in the reactor or the reaction we're using. And some theory, a little bit theory about safety, health, environmental issues, whatever. So you're probably asking yourself in what you're going to use this. You probably are almost done with your bachelor or something, whatever you're studying. Then you're going to use it a lot in plant design. So you're going to need to identify reactions and reactors in the process, which one are better depending on, I don't know, many important stuff like price, operation cost, if it's suitable for that type of process or type of materials. Also you need to do some improvements, change the conditions like temperature, pressure. Maybe you want to work with less recycle because you're having a lot of cost pumping that recycle stream, or maybe you want to increase conversion, moving this stuff here. So the thing here is that you're going to be playing with a lot of variables, and if you don't know how to operate or how reactors work, you will not be able to be moving conversion, temperature, selectivities, all that. And that's only about reactors. We are going to also see that we can change other kind of stuff. For example, about piping, about separation processes. Sometimes the limiting process is the separation process, so you want to sacrifice maybe the reaction or reactor conversion in order to get a better separation process, or at least not so expensive separation process. So if you don't know how this works, you cannot do this. You will be playing just like blind, moving conversion, temperature, pressure, recycle, and see how it interacts with the separation process. Also for pumping, I told you if you want to increase recycle for increasing a conversion, you're going to get, of course, more pumping needs. You're heating that stream, for example, it's in another temperature and you need another like lower higher temperature. You're going to need to heat or cool that stream, which is also implies money. And yeah, essentially that's an idea. I'm not going to explain you what do you see in plant design, but you need to know how the reactors work so you can get the whole idea of the process. And eventually it comes automation and process control. This is more about having a control in the process. So many times the reactor has temperature, level, pressure limits, and you want to automate that. If, I don't know, you increase temperature, then you add an extra stream so it can lower the temperature, or if the tank is pressurizing and it's going to explode, of course you need to purge that so the pressure does not go up and explodes. Or of course the level, if you're filling a tank or a reactor, it's filling and filling. Of course, you want eventually to stop or it will spill. So that's about automation process control. So if you know a little bit of reactors and you're controlling a reactor, I think you're done. Now, basic concepts you will need to know. I hope you already took this mass balance course. It's the most basic chemical engineering course. You need to know what's an inlet, a process, outlet, a consumption term here, the production, and accumulation for cases in which our reactor is not in steady state, like the batch reactor. And this is only a little bit. You need to know more. That's what I mean when you need to have taken this course before, so you can understand the application of the reactors. And of course, after mass balance comes energy balance. So this is good because you're going to understand, especially in the part of non-isothermal or non-isothermal reactors, you're going to have these temperature and energy requirements. So if you don't know how or why temperature and heat are dependent between each other, or they have something in common, or you don't know how to calculate the heat given a mass and a substance and a change of temperature, then I think it's not worth it to study because you're going to have a headache on the energy balance part. So please go and be sure that you've taken and you actually understand those courses. And heat transfer is only basic knowledge. Know how to, or how does heat transfer, convection, conduction, radiation, all those type of processes for heat transfer. Then a little bit about equipments. I don't know, maybe heat transfer or shell and tubes, heat exchanger, boiling or boilers, all those equipments, condensation, condensator, etc. That's not that of a must. I wouldn't say that you need to have taken this course, but will help you. If you already took it, then you're good. And the same for this one, momentum transport. We're going to see drop of pressure in fluidized reactors or packed beds. So you've probably seen the Ergun equation right now if you've seen the momentum transport course. If you have no idea, don't worry, we're going to see a small review. Yeah, as I told you before, with heat transfer, momentum is also a good thing if you've seen it before. If you haven't seen anything like this before, don't worry, we're going to see a small review. But a must is mass balance and energy balances. Good, now we are in the textbook and reference part. I took this book when I was studying university. I checked some forums and some other places. I think other people use, or universities use other books. We're going to see them. But essentially, the course is based on this book. It's the 4th edition. It's written by Scott Fogler, and the name of the book is Elements of Chemical Reaction Engineering. So essentially, it's about reactor engineering. As I put you here, this book is enough, so you don't need to buy another one. Of course, having more books will help you understand more. So these are the books I found that many other universities also use. I'm not going to use them in this course, but if you need more, a little bit extra information, or you don't understand how this author explains, you can check this, and I think they are good. Actually, this is the same author here, Essentials of Chemical Reaction Engineering. It's 1st edition. I think compared to this one, this is newer. Then Chemical Reactor Analysis and Design by Rawlings and Eckert. I just paged this book. It looks cool. I will still recommend this one, but if you have this or you need to do this, well, okay, it's not that bad book. It's okay. Yeah, essentially, be sure to get or to understand that the course is based on this book here. Now, you also need to know some chemistry concepts before. I'm not going to stop on that. Maybe I explain them a little bit when I'm doing the classes, but of course mole fraction, everything that has to do with moles, Avogadro's number, changing mass to moles and moles to mass. Please be sure to know that. You've seen mass balance, and energy balance, you should have seen that and you should know how to do it. So I'm not going to stop on that. Now conversion, fractional conversion, that's also seen in chemistry basic courses and in mass balance. So yeah, we're going to do a small review because it's important you actually understand it, but we are not going to stop that much in that. Now equation balancing, guys, you should know that since, I don't know, at least 3-4 years ago, so be sure you can actually balance an equation. Now limitant, excess reactant is the same thing, please be sure you know that. Arrhenius equation, you've seen it before maybe. It's about the temperature dependence of the reactor, the reaction. So we're going to do also a small review. It's not that difficult, so yeah, essentially it's everything you need to know, it's already covered. If you have doubts, you can always send me an email or a message and I will try to answer you ASAP. Now, of course, if you need some chemistry, you need to know some math, arithmetics, additions, subtraction, multiplication, division, percent, all that, change of units, please know it. We're going to see this method, Runge-Kutta method for differential equations. If you don't know it, it's okay, we're going to explain it here. Simpson rules, and this thing here, logarithm versus inverse plots. So you will see that there are many processes in which if you check the logarithm of that value and you inverse the other value, you will get a straight line. Even though when you just do this thing, you will get something strange. If you do this, you will get a straight line. So if you don't know it, okay, I'm going to do it also here. You've seen that also in the mass balance course. And yeah, essentially those are the basic concepts you need to know. Now let's go for the interesting part, which is the course structure. I like to do it like this. We start doing a molar balances for reactors. We see the type of reactors. We check how can we do the molar balances for that, and a small overview of the industry, how do they use them, maybe some videos or pictures so you can recognize them. Yeah, this is like the introduction part of the course. Now comes a little bit of theory. We're going to see how law and rates of data, how can we model that, or how can we use it from data. If you have experimental data, you can actually do some equations or get something like that. Now, once we got that, we're going to apply our knowledge, our previous knowledge, which is molar balances of the different reactors. Now we know how to get law and rates of reactions. So we're going to use that for this isothermal reactor design, which is temperature 1 equals temperature 2. And then we jump to non-isothermal reactor design, which is a little bit more complex because temperature changes. Then this implies there's heat adiabatically, or they can be also exothermic, endothermic. What else? About Arrhenius equations going to be changing with temperature, all that stuff. So a little bit more complex, but still okay. Then we go to some examples in transient state, not that much, just an overview. And then I like this part right here because it's only an overview, so you understand or at least know that it exists, how does it work, but we're not going to be that in-depth. So I will say half of the book is this part here, the other half is this part here, but we're just going to see a small overview of mechanisms, how catalysis work, reactors that use catalysts, diffusion, how diffusion affects, the distribution of residence times of different reactors, and what happens when you have non-idealities. Or what happens when your reactor, you suppose it's always mixing perfectly. What happens when you actually don't mix it? You have a gradient or something like that. We're going to use this chapter for those non-ideal reactors. So yeah, let me go chapter per chapter. I mark you here if it's only overview chapter, so don't worry if you see reaction mechanism and you're like, whoa, I don't have any idea of that, I don't want to see that. It's okay because we're going to see only a small overview. These are typically done in either reaction engineering for masters or in a thesis or in something more advanced. If you are really into reactor engineering, for, I don't know, research, some development of reactors, you will of course need to see this. But if you haven't, if you're just doing your bachelor, I think these ones here with overview between these parentheses, it's only like, okay, that exists, be sure that it what's about, and it's okay. So yeah, let me go for chapter 1, which is small balances. Very easy. This is the fundamental. Actually, I think if you do not understand this, you're lost, because everything is based on this. So once we got this mole balance, we're going to see conversion, and we're going to apply the conversion term to all the mole balances of the reactors. And then we're going to start doing sizing. How much volume, how much mass, how much everything, the diameter of the reactor, how much do you need to calculate for that. Then we pass to rate law and stoichiometry. Stoichiometry, as you know, it's a small review. Rate of law is how to get those mole balances with, or the mole balances depend on the rate of reaction laws. So how do we get them? Once we get that, we are set to calculate our isothermal reactors. So we're going to design volume, conversion, times, flows, whatever. Then chapter 5, collection and analysis of rate data. This is also the same stuff as, well, not the same, but it's similar to here. Once you get these reactors, you will need to get some rate data, either by experimentation or by analysis or other books. So that's chapter 5. Chapter 6, we start adding multiple reaction, which is exactly the same. We're just going to see some terms such as selectivity or yield. All those, we're going to understand why is it more complex to add two reactions, because sometimes one reaction is kind of fighting with the other reaction to get the best yield, so the best conversions, all does. So you, of course, you always want to get your best product more, and your not desired product not that much. So you're trying to improve this. So we're going to see how to favor some reactions. Now, I told you this is an overview of reaction mechanisms. We're going to see how the actual reactions take place, not just A plus B turn into C. We're going to see how A gets near B, and then they interact with atoms or electrons, and they form a double bond and all that. More technical, more into the chemistry side, not that much into the engineering side, but it's just an overview, guys, don't worry. Then we jump to the non-isothermal reactor design, which implies heat, temperature, and yeah, enthalpies, whatever. So that's why it's important you remember what's enthalpy, guys, from the energy course, because we're going to use that. Now we see a small overview of the how to calculate reactors in unsteady state or transient state, the same. Then we go to chapter 10, which is catalysis and catalytic reactors, also overview, just to know what's a catalysis, what does that do, and why do we use catalytic reactors. Then external diffusion effects and diffusion and reaction, also it's just a small overview of the problem of diffusion in reactor engineering. Then distribution of residence times is just about how the different reactors have different distribution times, and to see if they're ideal or you can model them or whatever. All those rules we're going to see, it's just a small overview of these residence times distributions. And at the end we're going to see how to model those non-ideal reactors. Once you know you have a non-ideality, you go and check for this reactor and for this non-ideality, how do we model that? So another time is an overview, because you're not going to be doing that. So you just need to know how to design volumes, conversions, all these parts here. It's okay. So all this part that says overview is just a small, to let you know that it exists, and if you are actually working in that, you already know Well, I've seen catalysis as an overview. Let me check out the whole chapter to see if it works or it helps me. And of course we're going to see some problems, exercise examples, and as you know, I always solve a lot of problems and post them in the videos section. You can see all the explained problems here. So if you are really into chemical engineering design and chemical reactor, you should check that out in the webpage. I'm going to put a link later. So yes, let's continue with the end of the overview. Finally, we're done. This was just a small overview of the course. At least you know what's the reactor engineering course like. So if you think it's useful for you, check it out. And if you think it's too basic, don't check it out, because you're going to get bored. It's going to be simple for you, especially if you're a chemist. I think it's good because you get to see the engineering part of the course, and if you're an engineer, well, of course it suits perfectly for you. And if you're in a master's, maybe it helps you to understand or to remember once again the reactor engineering course. So hopefully, if you're good in math, you remember well your chemistry, and you're good in analytical skills, you have no problems at all. So technically this is typical engineering or engineers properties: good in math, good in science, and good in analytical skills. So if you've seen mass balance and energy courses, which I hope, because if you're doing this and you have no idea of what is this, then you're going to have a bad time. You're going to get a little bit confused, but I'm not telling you it's impossible to understand. You're just going to be having a little bit more time to get the ideas. If you like chemical process, you're good. And yeah, once again, you need to practice, because theory alone does not help that much. So many times students tell me that they get the theory and then they see problems and they don't have any idea how to apply that theory. Please be sure you know how to do that. You want to check my webpage, I have solved problems there, so yeah, go there here and yeah, check them out. One very important thing I want to remind you: this is what makes the difference between all the other engineers and chemical engineers. As I told you, if you're a process engineer or an industrial engineer or a mechanical engineer, this course is the only thing that actually separates us from those engineerings. So if you understand reactors and you know how chemistry and all the chemicals, compounds and all that, you're going to be very differentiated from those engineers. So please be good at this. If you're not good at this, well, I'm sorry to tell you, but then you are not that so chemical engineer. If you need more information, just check this out. As I told you before, this is my webpage. Go to the courses if you're interested in the reactor engineering. If you just want to check some chemical engineering stuff, some chemistry, post, whatever, go and check the Facebook page, like it. And if you have any other doubt, just send me an email. I will gladly answer your mails ASAP. And finally, the bibliography we're going to be using is this one once again. Elements of Chemical Reaction Engineering by Scott Fogler, 4th edition. So that's everything for the overview, guys. Thank you for watching, and if you're going to stick around, please be sure to continue to the next video. We're going to start doing the chapter 1, the introduction to this all reactor engineering. I'm very happy for you guys. See you in the next video. What's up, guys? It's me, Chemical Engineering Guy. So if you like the video, why not push the like button? It really helps me to know if you're liking the videos, or if I should be changing something, or I should be adding something, taking out content, whatever. Also, sharing is caring. So if you got any kind of friends, teachers, colleagues, or whatever kind of person that might be interested in this type of content, why not share it? Sharing helps our community to grow faster in members and in content. If you want to keep track of my activity, videos, uploads, experiments, playlists, whatever content I'm getting on YouTube, be sure to click the subscribe button. Subscribing to the channel is totally free, guys. My dream is to create an online academy of chemical engineering, where everyone can access it in the world. Imagine a place in which the student, the teacher, and the engineer get the best of each other. So thank you guys for the support and the love.